Welcome to the third part of my mini-lectures on the definite integral. I call this part Modern Times because the focus is on how computers can be used for the approximation of definite integrals. Essentially, there are three ways to calculate definite integrals. One, if the function can be integrated, if we know the antiderivative, we can use the fundamental theorem of calculus. Unfortunately, this is not always, not even often, the case. Two, one could look at the finite sum, try to find a closed expression, and then go for the limit. Archimedes did something similar, but without the limit considerations, for his treatment in the parabola case. This method is very often similar to the method 1, just a discrete version. Number 3. Or one could go for approximations and calculate finite sums of areas of rectangles. Here are the advantages and disadvantages of this method. It does not work if the expression contains parameters, not even something simple like the integral of kx squared dx from 0 to 2 could be attacked in this way. Second, the method is not exact, just an approximation, however, as precise as we want it to be. Then, the method works for every function, definitely an advantage. And finally, what was a very tedious calculation for centuries, a disadvantage for many years, can now be done in seconds using computers. Not even advanced programs, you just need something very simple, allowing you to multiply and add, as we can see. Since most of you are not mathematicians, you might not care so much about parameters and preciseness. For most practical purposes, a fast calculation of an approximation is all we need. Let me show you how you can create an Excel sheet template which you can use to calculate definite integral approximations for every function. At the end, you want to have only 3 fields where you input something, x, the starting point x, the a essentially, f of x, the function itself, and delta x, the increment by which you use for the Riemann sums. Okay, so here on the first column, I want to have all different x values with difference delta x, so you have x0, x1, x2, x3 and so on. In this column I want to see the corresponding y values, so y0, y1, y2, y3, or f of x0, f of x1 and so on. Here I have a column for the products. Remember, the products are the areas of the corresponding rectangles, and in this field I want to have the sum of these sum of the areas of the rectangles, which is the approximation for the definite integral. Let us start by putting in some values here. So let's say we are doing the integral from 0 to 2 of f of x equals x squared. So that means our a is 0, I plug it in. And here's the formula. So remember, in Excel the formula is used by referring to the corresponding x value. So here I'm just writing equals a4 times a4. So I'm clicking on it again. This is now x squared, obviously. Then I need a formula for the next x, and if this is my x0, then of course x1 would be x0 plus increment. So here the formula is equals the previous x value plus the increment. So I'm clicking on C1. Now here you have to be careful. If you use this formula, then you cannot copy and paste it down, because here something is used which is called relative referencing. What we actually need here is absolute referencing. That means we need to write a $sign in front of the 1. We could also put a $sign in front of the C, but it doesn't really matter much. This means that if you copy this formula down, it will always be C1. It will change to A5, A6, A7, which is good, but it will always refer to C1. So this is the formula we use here. Of course, what we do here is we copy this formula. So in a sense, I'm maybe copying and putting the formula in here. Actually, I'm using something like copy special in English, because I want only the formulas to be copied. Otherwise, I would get this yellow field here. So I use this one. And you see, I have 0.01. The square of 0.1 is 0.01. And of course, here the formula is f of x times delta x. So I'm just using this formula equals f of x times delta x. And of course, the same, for the same reason as before, I have to pin the 1. So I write P4 times C $1. Okay. Now let me copy these numbers down, and you see if I copy them down, I will get the different x values, x1, x2, x3, all this increment of delta x. Actually, let's also go from 0 to 1 here in this example. Here, if I copy this formula down, oops, let me do it properly. I take the handle and pull it down. We get the squares of x, of the x values, so we get the y values. And here, of course, this is also copied down using the pull down, and we get the corresponding products. Now the integral, of course, is a sum of all these blue values, the products f of x times delta x. Remember, these are the areas of the rectangles. Since we want to have this sheet to be flexible, we want to have not only 10 rows, but maybe 100, 1000, 10,000 rows. It might be a good idea to add from the beginning everything from cell C4 up to cell C4000. Then we can include at least 4000 cells. So here what I'm typing is, I'm using the formula, and this is a German version, so I have to use the German one. But you would use sum, and I'm going from C4 up to is done with colon, and I'm going up to, let's say we're going up to 10,000. Why not? That's not much of a problem for Excel to do it. So we are adding the values in the C column from row 4 up to row 10,000. So we can really have many rectangles if we want to. And now let's go and see what we get. So we get an area of 0.385. So that means that the approximation, the first approximation of the area under the function f of x equals x squared from 0 to 1 with increment 0.1 is 0.385. And of course, remember that that theoretical value would be 1/3, so 0.333. Now we can get closer to the theoretical value by just making the increment smaller. So let's go here and change this into 0.01. So now we are having 100 rectangles which we want to add. Now, you see, this changes funnily. What you need to do, of course, is we need to go now 100 values down. So we go up to, let me see how far we go, 105 or something. Because, yeah, actually 104, you see, 0.91, 0.92, and so on, up to 1. And of course, the other columns we also have to pull down accordingly. So we just make the area much longer. And now let's see what we get. 0.33835. So that's not bad. Remember, it's supposed to be 1/3. What about 0.01? Let's try to make it a little more precise. Again, we need to move down from here to 1. So this is about row 1005 maybe. Takes a little time to find it. Let me see. Where is it? 1005. No, actually 1004 it is. Now we have to do it for the remaining 2 columns. Again, grabbing it, copying down up to where x is equal to 1. So now we have 1000 rectangles, each of this 0.001. Let's see what the approximation is. Now you see it's 0.33383. So this is rather close to 1/3. So you can see we can get closer and closer approximations of the integral by just making delta x smaller and smaller, grabbing the numbers and pulling them down as much as needed, and everything will fall into place automatically. Now as for the template, what you want to do if you have done this once is, if you want to play around, then of course there are 3 parts where you can change. You can change the increment. I have shown this already to you. Of course, you can change the start value. So let's say we are doing the integral of f of x equals x squared from 1 to 2. Then I'm just changing my a value of my beginning x value to 1. And you see, or you should see, that we are going up to 2, of course. So if I'm scrolling down all the way, the last value would be a 2. And the integral is 2.33583. Well, probably 7/3, I think. So this is how you change your a value. So this is how you change your increment. Keep in mind, if you change your increment, you also have to check whether the last x value in your column is a b value until which you want to integrate. If not, then you have to either pull it further down or you have to delete something. And the other thing which you can change here is you can change, of course, the formula here. So here, so far we have x squared, but we could also do the function, let's say, e to the power of x, or exponential function of x. And of course, it's not x, it's we go to a4. So the formula is exponential function of a4. a4 is where the corresponding x value is. You can see it here. And again, we could copy this down. Maybe copy paste special, because I want to maintain the color. So I'm going to this one value here, plugging in the formula. And then, of course, I can choose this one and pull it down up to 2. So this would be now the formula, or the approximation of e to the power of x from 1 to 2. Let me see where my 2 is. Here it is. What is the corresponding integral? Well, this is the approximation of the integral. So save this template, and you can approximate every definite integral as closely as you want to. Just choose delta x smaller and smaller and smaller. Just pull the columns down further and further and further. And yeah, of course, here you plug in your function. Here you plug in your starting x value, and you pull down until you achieve your ending x value, which is a b value.